everybody? Good. Good week. Anything happening at work we need to talk about? Nothing? You working? Huh?
Partly.
A little bit. All right. So, what we want to do tonight is get out our homework, which was our first piece of paper. Starts off question number 1, purpose of blank. So I want to go over that and kind of answer these together. But this is just kind of a summary of section 1, which takes into account what we did last week and takes into account what we're going to do tonight. So kind of fill in the blank. So y'all help me fill in the blank as we go, and we'll kind of go through each one. So number 1, matter of fact, somebody else can read it. I don't need to do all the reading. Y'all kind of take turns. So James, you do the first one. You can leave it blank, and then you do the second one. We'll go on back over and forth.
The purpose of blank.
If you know the answer, go ahead and
Okay.
tell it.
The purpose of feeder circuit load calculations is to determine the size of feeder overcurrent protection devices and feeder circuit conductors using NEC requirements.
Okay. And our feeder circuit, we've determined as well. Where is our feeder circuit?
To the last overload protection device.
Up to that, like feeding a panel, or feeding, all those are feeding, up to that last overcurrent device. Okay, they're feeder. Okay. All right. So number 2, Nate.
The service drop, the overhead conductors between the utility electrical supply system and the service point.
Yeah, let me make sure. Is that what you got, James? No. I'm trying to find mine. Hold on a minute. I'm trying to get to my answers as we go. Number 2. Number 2 is service drop.
Yeah,
It is, yeah. Service drop. Very good. We find that in our trade terms or definitions. Okay. Overhead, and that makes sense. Overhead service conductor. We talked about it last week. We drew it on the board. Overhead conductor between the utility service supply system and the service drop is when we have our meter, and then overhead with the weatherhead, and then our wire. That's our service drop. Okay. All right. Number 3.
Electrical calculations can be divided into 3 sections: branch circuits, feeders, and services.
Yeah. Branch circuits, feeders, and services. Okay. And services. All right. Number 4.
NEC 110.14C includes blank for terminating conductor. And
James, you can help him out.
temperature limitations.
Temperature limitations. Okay.
That's what I was thinking.
Okay. So what do we mean by temperature limitations? And what are we talking about?
That's the, the heat overload, like you said, more than 3 circuits in a pipe or something. 3
Yeah.
current carrying conductors in a pipe,
Okay.
start heating up with pipes, so certain
Yeah.
limitations on that.
And what else it does is in 310.15b16, which is our main part of our code, we have 3 columns. We've got a 60 degree, a 75 degree, and a 90 degree. And under 110.14c, we see that, under 100 amps, it's 60 degrees, right? That's what we use, 60 degree wire, regardless of what the insulation is. And then over 100 amps, we use 75 degree column. And usually there's very few instances where you'll use the 90 degree column, because very few terminations are above 75 degrees. And so therefore, matter of fact, we can, if you want to, let's turn to 110.14. Let's just go ahead and turn to that in our code book. You may have to go over there. I ain't got no code book. C1, number 1, the termination provisions of equipment for circuits 100 amps or less shall be used for one of the following. And you see that conductor is rated 60 degrees Celsius. And you go down to the small letter B, termination provisions of equipment for circuits over 100 amps, marked conductors larger than number 1, or marked conductors larger than number 1, shall be used only for one of the following. Conductors rated 75 degrees. So both of those things, over 100 amps, larger than number 1. And also notice, if you just kind of, while we're looking there, number 4, under equipment provisions, it says for motors, designation B, C, or D, conductors have an insulation of 75 degrees or higher shall be permitted to be used, provided the ampacity of such conductors not exceed 75 degrees. So, so anyway, so that's where we get our temperature limitations from. And that's an important part of the code right there, 110.14c, because it keeps us from being confused as far as what we use. Main thing to understand, over 100 amps, under 100 amps. You got that, we're good. Okay. All right, number 5.
When the overcurrent protection for a conductor is located at the load end instead of at the supply side of the conductor, the NEC generally that to be a tap.
Okay. All right. Overcurrent protection. Okay. Overcurrent protection, number 5. Okay. And what are examples of overcurrent protection?
Fuses and circuit breaker.
Fuses, circuit breakers. Okay. That's pretty for the overcurrent. What's an overload protection device? What is that? Usually a what?
Motor relay, heaters in it.
A heater that has heaters in it. That's an overload. Okay. All right. Number 6, the 10-foot tap rule is found NEC what?
248 or 240.21B1.
240.21B1. 240.21B1. 10-foot tap rule. Nice. And then we have, and we'll talk about 10-foot tap rules in just a little bit. About and a lot of, matter of fact, you'll see one of the things we'll be talking about 10-foot tap rule is on a transformer. But we do have 10-foot tap rules, especially when we're going to have, we may have a feeder coming out, we may set a junction box. I think we talked about this last week, whereas, we've got a feeder coming out, we set us a gutter, we want to feed more than one motor, let's say. Okay. And the 10-foot tap rule is applied to this right here as far as governing how we size that right there. Okay. All right. And 25-foot tap rule is found where?
Section 240.21B2.
240.21B2. Okay. All right. Number, and we don't need to discuss that anymore right now. Number 8.
NEC 240.21B3, this specific conditions for the application of the transformer 25
Yeah.
tap.
So number 8, 240.21B3, the specific condition for the application of the transformer. And we'll get into that later too as far as some examples of that. Transformer. A building is defined as a structure that blank.
Stands alone.
Yeah. Stands alone. We talked about that last week. Firewall, building, stands alone or separated from adjoining structures by firewalls. Okay? We may have a shopping center. It has multiple tenants, right? And because of the firewall, we can actually put in a separate meter for each one of those tenants. It becomes its own building. Okay? Because supposedly on a building, you're supposed to only have how many services? You only should have one, right? There's special applications, special circumstances where you can have more than one. But for the general part, and why do we want just one service?
case the building catches on fire, you gotta wanna be able to shut it off
Yeah.
before you go in.
We want the fire department to be able to find the source of power and be able to cut it off all the way from one spot, so makes sense from a safety concern. Okay. All right, number 10, underground service conductors go between the service point and the blank.
First point of connection.
First point of connection, yeah. First point of connection. Underground service conductors go between the service point and the first point of connection to the service conductors in a terminal bus. Number 11,
The minimum feeder circuit conductor size before the application of any adjustment or correction factors shall have an allowability capacity of not less than 100% of the non-continuous load plus 125% of the continuous load.
yeah. So, and that's the thing to remember. We always have 100% of the non-continuous load and 125% of continuous load. And we'll get into what is continuous loads. Motors, for the most part, are continuous loads until it's tell you not. Commercial facilities where lights are going to be on all day, you know, because what, 3 hours continuous duty. So signs, a lot of things like that consider continuous duty. Okay. All right. Number 12.
A building or portion of a building in which one or more self-propelled vehicles can be kept is a garage.
Yep. Read it again. A building or portion of a building which one or more self-propelled vehicles can be kept is a garage. Okay. And the reason we need to know that because there's different wiring methods for garages. Okay. And that's why we need to know that. And we'll encounter that a little bit later too. Okay. Number 13.
When derating conductors, it is permitted to use the allowability capacity listed for the temperature rating of the conductor insulation instead of the selection and passage.
All right. Let me find it in my book here real quick. 13, verse 13. Where'd you find it at, James? I'm looking for it. I'm looking right over it, I'm sure. 13, okay. 13 is on page 2. Okay. When derating conductors, page 2, about the last paragraph. Matter of fact, that was a paragraph that I actually told y'all to highlight. Yeah. So derating, and so I want to read that whole paragraph actually, because I think it's important for us to hear that again. Listen to this paragraph. When derating conductors, it's permitted to use the allowable ampacity listed for the temperature rating of the conductor insulation instead of the selection ampacity, which is restricted to 60 degrees or 75 degrees. For example, the minimum size THHN copper permitted to supply a load on 125 is number 1 based on 75 degree column. When derating this conductor, the ampacity will be 150 ounce because you can actually use, this is the one time you can actually use the actual type of wire insulation it is, and so therefore on THHN you can use the 90 degree column, which helps. So I think that's an important paragraph right there. I think I told y'all to highlight that. All right. Number 14.
NEC 220.12 provides specific information for determining lighting loads for occupancy.
NEC 220.12, okay, and that's found on page 12. NEC 220.12 provides specific information for determining lighting loads for occupancies. And there's a table we'll get to. Most, like a dwelling is 3 VA per square foot. And there's other different entities in which, you know, it varies whether it's a restaurant or whatever it is, and we'll see what that table is a little bit later. Okay. All right, number 15.
Demand factors for neutral conductors can be found in NEC section 220.6, 61,
Yeah. Okay.
C2.
Yep. 220.61. That's the primary place. So 220.61 is good enough. Okay. And C2. Okay. But if you go to 22061, C2 is found inside of 61. So 22061 is good enough. And that's found on page 11. Number 16.
The total load placed upon certain feeders may be reduced by applying demand factors.
All right, the total load, and that's found there under demand factors. So the total load placed, and it should be placed, should be a D there, placed upon certain feeders may be reduced by applying demand factors. And if you look there on page 11, there's a lot of NECs there. There's a list of them, a laundry list of about a dozen or so, starting table 22042, which is talks about general lighting load demand factors, 22044 for non-dwelling, 22054 household electric dryers, 22055 ranges, household cooking appliances, 56 kitchen equipment other than dwelling, 82 optional calculation for a dwelling, 83 optional calculation for existing dwelling, 84 multifamily dwelling, 86 optional method, and so on and so forth. So y'all get the gist of it. So demand factors. And because of that, you can see there's a lot of demand factors that exist that actually affects the size of wire we use. So it comes into play. Most of the time it's not something y'all do in the field. I mean, it's something that's calculated for you, before you get there. But it's not, doesn't hurt to know, in case really something looks out of order. Or you may be wondering, why am I pulling a number 8 wire to this receptacle? Now, common sense says you're not going to hook up that number 8 wire to that receptacle, right? I hope not. Right? Okay. What are you going to do?
Just put me a little pigtail on it.
Yeah, you're going to put your pigtail on there. But that receptacle ain't going to hook that number 8 wire, right? But, good. So we know that. All right. Number 17.
Use of the 100-foot tap rule is limited to installations in a high bay manufacturing building with a wall height of over 35 feet.
Yeah, and that makes sense, that 100-foot rule, 35 foot, but you got to go, regardless of what you do, if you got 100 foot, you got to go up 35, and you go over and you got to go down 35. That's already 70 foot. So it doesn't allow you but 30 more foot. So and that's that you see that where we read that there, and you see it. I mean, it just makes sense. And you read there, it says use of the 100-foot tap rule is limited to installation high bay manufacturing buildings over 35 foot. And most of the warehouse we do, it's right at that. It's not over 35 foot. It's actually 35 or a little bit below. 30 to 35 is generally the area that we work in more. And it says there, this section lists specific conditions for the application of the 100-foot tap rule. And you can read what it says there. Okay. All right. Number 18.
NEC section 240.21C provides the installation and length requirements for the secondary conductors of a transformer.
Yeah. Of a transformer. That's found on page 10. NEC 240.21C provides the installation and length requirements for the secondary conductors of a transformer. Okay. Number 19.
NEC section 240.21C6 will permit secondary transformer conductors in lengths up to 25 feet when certain conductors are met, conditions are met.
Yep. So we go to NEC, we were to go there, we won't go there now. 240.21C6 permits secondary transformer conductors in length up to 25 foot when certain conditions are met. And the conditions are actually listed there. On page 10, there's actually 3 bullet points there that list those conditions. Okay. Number 20.
Transformer secondary conductors are considered taps.
Taps. Transformer secondary conductors are considered taps. Okay. And we found that on page 8 and the little bullet point there. And that's found, it says section is 240.21C. Matter of fact, if you read that, it says transformer secondary conductors are considered taps as much as limited in length to not more than 10 foot, 25 foot, depending on the application and located inside the building. Number 21, the K factor for copper is blank,
12.9.
12.9. And what is the K factor? What is that? Any idea? Take a stab. What is the K factor?
Resistance per foot of conductor.
Yeah. No, not really. The 12.9 actually represents the constant. Yeah. Copper, we have, when we're doing voltage drop, one of the things we have to put in there, like when we're doing calculations, one of the things is a K. And so it's called the constant. 12.9 for copper, aluminum is a different number. And it does have to deal with resistance because 12.9 in copper, whereas aluminum is higher. It's like 21.3 or 21.2. Is that there listed in our book somewhere actually? I think. Where did you find that at, James?
I found mine, and it's on page 4.
Okay.
It's in the little bulletin down below.
Yeah, there we go. It just says copper. It doesn't actually give us aluminum, but I'm pretty sure it's either 21.2 or 21.3, something like that. I got it wrote down somewhere. But that's close enough. But what we're doing tonight, we'll be dealing with copper, I think. Okay. And to find resistance, as a matter of fact, if you want to look in your code book, chapter 9, table 8. Turn to chapter 9, table 8. And it's on page, well, you got a different code book than me, but if you look there, it gives us, under chapter 9, table 8, under copper uncoated, it gives us ohms per 1,000 feet. So that gives us our resistance. Okay, it gives us our R. The area we find there, the inches squared. We find circular mills. That's doing voltage drop. That's one of the things we need to do calculations is circular mills, isn't it? Okay. What's the circular mills for 250 MCM? KC Mill.
250 or 250,000.
250,000. Trick question. Because it's actually not listed, is it? Okay. There's 250,000. Okay. And so any of those listed below that is itself times 1,000. That's how you get to KC mills. And that's what the K stands for, right? 1,000. Yeah, so it makes sense. Okay. All right. Continuous duty load is a load that operates without interruption for more than blank hours straight. 3 hours straight. The conductor from the service point to the service disconnecting means is called blank blank.
Service conductors.
Service conductors, found under the definition of trade terms, page 1. Overhead service conductors go between the blank blank and the first blank 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 to the service entrance conductors at the building or other structures.
Service point and point of connection.
Service point is our first two blanks. Point of connection. Okay. So overhead service conductors go between the service point and the first point of connection to the service entrance conductors at the building other. Okay. Does that make sense? And last question before we get started in our section tonight. A blank is defined as the value by which you multiply a number in order to obtain a result of 1. For example, the reciprocal of, I shouldn't have said that. For example, the reciprocal of 3 is the third. So what's the answer?
Reciprocal.
Reciprocal. I should have left both of them blank. Okay. I think we did that last week.
Yes.
Okay.
And then I still read it. And
Yeah.
then my mind just went blank because it was my last one. And I was sitting there and I was looking, and then I looked back and I read the question again. I was like,
Yeah, I
dummy.
mean,
You're
dummy.
a big dummy.
Yeah, the answer's over there. So, all right, so we're going to start tonight. So that's a review of really what we talked about last week and what we're going to talk about tonight. We're going to start on page 7, section 1.2.0, calculating feeder ampacity and we need to get through the intersection, which is through page 13. And there's not quite as many calculations tonight, so it's just more of a reading and understanding that. So I'm going to actually ask sometimes for y'all to read rather than me. So when you do read, try to speak up so everybody can hear you. But the first thing we're talking about, 1.2.0, is feeder ampacity, calculated feeder ampacity. And, you know, it gives us an equation here. I is equal to VA over V. Okay? And what are these symbols stand for? What does I stand for? Yeah, current or amps does. Volt amps is just, that's volt times amps, right? That's really what that is. So the V is volts, volt amps. And of course the V is volts. So if we look there on page 7, it just gives us an example there. Because for example, and it's a single phase now, single phase, that's important. For example, the ampacity of a single phase 240 volt load, if that's our voltage, that's our V, rated 2160 VA, or volt amps, is determined by dividing, and so that's what we got. We got VA is 21,600, and our volts is what? 240. Now that's actual voltage. That's very important when we say actual voltage, because that's the that could have been single phase 230 volt rated motor. But if you're single phase, your actual voltage coming in is what? 120 what? 240. So you got to use 240, not 230. Okay. Don't use a rated motor. Use the actual voltage. Okay. And so 21,600 in the 240 is we're gonna get the I, which is equal to the I, which is equal to what? If you do the calculations. Somebody do the math. 90. If you wanted to check yourself, you would multiply 90 times 240, wouldn't you? And hopefully you get 21,600. And because amps, because all you're doing is amps, and here's the thing, is amps times volts is equal to volt amps. That's all you're doing. That makes sense? Amps times volts, which is really what it is, or volt amps, or volts times amps, you can do either one, is equal to volt amps. Okay, that's what volt amps, but what's another word for volt amps? What would this actually be? What's another word for volt amps? What is this?
It's a watt.
This is watts. Okay. So amps times volts equals watts. And volt amps is the same as watts. Okay. So, page 8, we're looking over. Now here's the next thing. That was single phase. So we get into 3 phase, we get into square root of 3. Okay? And the square root of 3 is what? 1.732. You can either use it on your calculator, you can do the square root of 3, or you can actually fill in the blank, 1.732. So it gives us an example there. It says we got a 208 voltage, 3-phase, rated 15,200 VA. We know that the VA is going to go on the top by this here. Our voltage is going to go on the bottom. But now, instead of just doing 208, we got to do times 1.732. And I think if you'll do that, that comes out to about 360. I think that's just one of the numbers you memorize. Am I right? do 208 times 1.732 and see what you come up with. 359.
360.26.
Yeah. So we'll round it off to 360, and so now, rather than have to do that every time, you know that 208, three-phase 208 is 360. Just the easy way to remember. Or you can multiply it out every time, it doesn't matter, whatever you're gonna do. And so now, we're gonna take 15,200 and divide it by 360, and we're gonna get how many amps?
42.
Yeah, 42.19 amps, or 42. 42 amps. All right. Look at example number 1. We'll just kind of go through these. I probably won't, unless I need to put them on the thing that I won't, because they kind of reiterate what we just talked about. Example number 1, and here's the key thing, is we're looking for single phase or three phase. And here's something we got to do too. Okay, we're going to have to change something. If you look at example number 1, it says, what's the ampacity of a single phase resistance load with a nameplate 42.5 kW. Now they give us kW. Okay, and it says it's 240 volt. That's one of the things we know, and we know that it's single phase, don't we? That's what we know. So what do we have to do now, guys? We got, how are we going? We know that at I is equal to volt amps over voltage, so we actually got voltage at 240, right? What do we do to this 42 and a half? Multiply it by 1,000. So this kW. There's the K. So 42.5 times 1,000 is what? 42,500? Now we divide it, and we should get what our average is. Which is how much?
177.08
Yes. We'll call it 177 amps. Now, the main thing that I want you to get is this right here. You see what we're doing, James? 42.5 kW. That's kilowatts. Okay? That's kilo. That's what the kW stands for. Kilowatts. And so the only way we can get it, we've got to be able to get the volt amps. And volt amps is watts. And so the only way to do that is get rid of the K. And the only way to get rid of the K, just like we did on chapter 8, just earlier, or chapter 9, table 8, you got to multiply that 42 and a half by 1,000. Then that gets rid of it, and that actually just makes it, when you do that, that actually just makes it watts. Make sense? Example number 2, what's the ampacity of a three-phase panel with a calculated load, 135 kVA, same thing, 208. We got to do two things. We got to do 2 steps. Okay. We got to do 2 steps. What are we? First thing we got to do? We got to take that 135. We got to change it into what?
135,000.
Right. Alright, that becomes our watts or our VA. We'll multiply it times our voltage, which is what? 208 times what?
1.732.
Yeah. And what we want to do is multiply this out first, which would give us like 360, and then we divide this and see how much we get.
Should be 374.72.
Yeah. We'll call it 374. Easy enough? The main thing, remember this formula right here. Okay. And it's actually, if you got a pie chart on your code book, okay, it should be under there because we're actually solving for I. And if you look there, power, I is equal to P over E, and power is watts. And E is what? Is voltage, right? So it's no different. It's just different symbols. Okay? We just got to remember what those symbols stand for. So I is equal to P over E in our you know, and there's a little wheel here. And power, watts, you know, VA, all the same thing. E, again, is what? Or V, E is what? E is voltage. So that's where we're getting this from. It's from our formula, our wheel. We good? Let's do number 3, and we'll take a little break. Take a little 5-minute break. Okay. All right. Number 3, what size THWN copper conductors are required to supply the primary of a 75 kVA 3-phase transformer? The primary line-to-line voltage is 480 volts. If you look there, solution says 75 kVA, okay, times 1,000. That's the first thing we have to do. Times 1,000 to give us 75,000. Okay, that's the first thing. What is their voltage? Tells us what is their voltage.
480.
Yeah, 480. Let's do it here first. 480 times 1.732 is how much? Like 830, I can't remember. Is it 830?
$831.
836, okay, and 830. Okay. So now we're going to take that 75,000. We'll change paper here a minute. 75,000 and divide it by 831 already. And we should get what?
About 90.
About 90 amps. Again, the key thing is when you're doing 3-phase, don't forget that right there. That'll ruin your day. You did that. And why are we actually doing this? Because if you think about it again, if you think about 3-phase, and we're talking about 480, we know that we got 3 phases. If we go, one leg is what? On the 480 is 277 volts, right? Okay. But if we go between 2 legs, how much do we have?
400 maybe.
Okay. Multiply 277 times 1.732, see what you get.
$479.77.
Which is
480.
480. So that's all we're doing. You see, we know that each one of these legs is 277. But when you read between the 2 legs, you get 480. You get 480. And 277 times 1.732 is 480. So that's where that's coming from. Makes sense? And of course, square root of 3, we got 3 phases. And that's the reason behind all this math here. Okay. All right. Let's just, I tell you what, let's go on, let's finish that page. Then we'll take it back. Then we'll get into some tap rules. All right. Let's read on there. So it actually asks us for the size wire on that one. So we're not done. We're down to 90. It says, and now let's go to 310 15B16. 310 15B16 in our code book. B16. Now, it says here in the book, it says number 3, THWN. Matter of fact, it said THWN. If you look here, you find THWN where? On the what? 75-degree column, don't you? But this is only a 90 amp load. But if, and it says it there in the book, if your termination is rated, and most of the time that's written on the lug, how much it's rated for. So if that termination lug is rated for 75 degrees, we already know that the wire that we want to use is 75 degrees, and we're looking for something that'll hold how many amps? At least how many amps? 90 amps. Then therefore, if both were 75 degrees, we know the wire is, if the termination is 75 degrees, then we could actually use number 3 wire, couldn't we? Okay. If not, if you read there, then number 1 would be required. Because if not, we have to go back. I'm trying to think. I'm stopping myself for a minute, asking myself, why number 1, why not number 2? I think I disagree with that. If not, then number 1 would be required. Where I really think, if not, I thought we'd drop back to the 60-degree column. And number 2 is rated for 95 amps, isn't it? So I disagree with that. I'm gonna question that right there. I think it's actually number 2. Not that matters, right? But the key thing is when you're in the field, and because it'll be on there, whether it's a lug on a transformer or or lug, whatever, mechanical lug. If you look at it closely, there should be a terminal rating on there. Okay. If not, then you have to go back to this 110.14c, and you have to use either under 100 amps, which puts us in the 60-degree column, or over 100 amps, or number 1 or larger wire, which puts us in the 75-degree column. Right? Yeah. I'm just thinking through why they might have used number 1, but I can't come up with a solution. All right. Let's look at example number 4, and then we'll take a break. What's the secondary current of a 1500 big transformer? 1500 kVA 3-phase transformer with a voltage, so they want the secondary, with a voltage rating of 482.77. All right. Multiply 1500, it says multiply 1500 times 1,000. Okay. And the secondary is actually, the secondary rating is 482.77. So we got 1500 times 1,000, which is what, 150,000? Is that right? No, it's more than that.
It's 1,500,000.
Yeah. 1,500,000. Thank you, Jamie. 1,500,000, and we're going to divide that by what? We've already come up with a number that we actually should be dividing that by.
Should be 400.
480 times 1.732, which is what, 831?
Yes.
So let's divide that and see what we come up with. Yeah, 1,804 amps. So really we're doing the same thing, kind of repetitiously. The biggest thing is understanding, A, anytime you got KVA, make sure you change it to 1,000, and B, make sure that if it's 3-phase, that you're looking at your primer, at your voltage, 480, when it says 482.77, your 480 represents your 3-phase leg, and so don't be mistaken in multiplying 277 times 1.732, you'd be wrong. And like 122.08, you're always doing the 208 times 1.732. So the 208 or the 480 represents the voltage in between the legs, not each leg. Okay. All right, let's take a little 5-minute break. And I'm going to put us on pause.